Welcome to section 9.1, Exponential Functions. Today we're going to talk about exponential growth and decay and what these graphs look like and what they actually are. So exponential growth is when something gets larger over time. So sometimes you hear the phrase, it grows exponentially. People throw this phrase around a lot, but what we're really talking about is it goes up by a certain amount. This amount is based on an exponent. What the graph of something that grows exponentially looks like is it'll start very small and it'll continue to get larger and larger, and it is a function. Okay, so we want to note that. So that is exponential growth. It grows, it gets larger. The second one is exponential decay. Exponential decay is when it gets smaller. It decays. You think about in science when you talk about certain things decay. They get smaller, they go away. So what exponential decay is when something gets smaller over time. This would be something where you would say it starts large and it's getting smaller as we move left to right. And again, it is a function as well. An example of this in science is the half-life. So if you've gotten to that in chemistry, something gets cut in half each time every year, and then it slowly gets smaller and smaller based on what year it is. So that's exponential decay. It gets smaller over time. So when looking at these individually, I'm going to look at growth first. They're going to be set up in the form of an equation, and it's going to look like this. Okay, and actually both of these are going to be set up in a similar format. So it's going to be y equals, and then a and b represent numbers, and then x will always be a constant. So x will always be there, y will always be there, a and b will be numbers. When looking at exponential growth, and remember this is the graph that goes like this, it grows exponentially, it gets larger over time. What we're concerned about is this b value. Okay, certain characteristics will make this b value and make it go up each time. Certain values for b will make this decay and make it go down over time. So what we're looking at here is an example of this would be y equals a, let's see, instead of using a, let's just use a number, so 5, and then we'd say 6 to the x. If you type this in your graphing calculator, you would get a growth function solely based on the 6. So the b is what we're focused on. It's being raised to the x power, so that's how we identify it. So b is huge. If b is larger than 1, okay, so b is larger than 1, it is an exponential growth. And the reason being is this number right here, if it's larger than 1, when you raise it to a certain power, like 6 squared will be 36. 6 to the third will be 216. Okay, so we're going to get exponentially larger here. So if this b value, the number raised to the x, is greater than 1, then that number will always continue to get bigger no matter what power we raise it to, as we raise it to larger powers. On exponential decay, you will also look at the b value. So an example of an exponential decay could be this. So when we look at that b value, the b value is a fraction, it's less than 1. Okay, so when this b value is less than 1, if we raised 1/2 to the first, we'd get 1/2. If we raise 1/2 to the second, we'd get 1/4. If we raise 1/2 to the third, we'd get 1/8. We would get exponentially smaller. So if you multiply fractions by itself, you're getting a smaller number. You're taking a fraction of a fraction. So in this case, b has to be less than 1. So really how we identify these is based on what's in the parentheses and what's being raised to the x power. Okay, identifying whether each of these is growth or decay, I want you to quickly do this. I want you to hit pause, and then I will come back in a couple of seconds. A is a decay. and it's a decay because of what's being raised to the x power, 1/5. Whenever you do 1/5 times 1/5, you get 1 over 25. And if you do that again, you get 1 over 625, or 1 over 125. Okay, so it's going to get exponentially smaller. On B, if you do 1.2 and you keep taking it times itself, it'll be a growth. B is greater than 1. Decay, B is less than 1. In this section, we're also going to solve exponential equations. This top part is kind of like the logistics of it. If b is a positive number other than 1, so if b is 1, then this isn't not going to apply. And I think that's obvious because 1 to a certain power equals 1 to a certain power. You could have 1 squared equals 1 to the first. So that's just ruling out why that doesn't apply. If b is something other than 1, what we can say is these exponents, if they're set equal to each other, then x is equal to y. Okay, so we're going to take this and we're going to expand on it a little bit, but that's the basics of it. We have two bases that are alike, they're set equal to each other. We say these exponents have to be equal as well. So here's an example. First off, we want to just look at the setup of the problem. It's 3 to an exponent, it's 81. So what we want to do is we want to write these as something that has the same base. So here we have base of 3, and we have 81. We want to rewrite this 81 as 3 to a certain power. And thinking about that, 81 is 9 times 9. So 3 to the 4th is 81. Okay, so now we have written, again, we've taken 81, we've rewritten it in a different form, and now we can set these exponents equal to each other because we have like bases. So doing a little bit of Algebra 1 basics, we get n is equal to 3 over 2, and you can easily plug that back in to ensure that it's correct. The next example, we have 4 to a power, we have 8 to a power. This one's a little trickier because you can't just change one, you're going to have to actually change both of them. So what I'm going to do is, instead of 4, I'm going to write it as 2 squared. And instead of 8, I'm going to write it as 2 to the 3rd. And remember, these are all being raised to these certain exponents, so we have to realize that. Okay, now we know power to a power, you can multiply this. So you can have 2 to the 4x. Power to a power, you're going to multiply this. So you'd have 2 to the 3x minus 1. Now that we have like bases, we can set our exponents equal and solve. And x is equal to -3. So we did the last problem where this was an equal sign. It also works when it's an inequality. Okay, so instead of an equal sign, we're just going to use the inequality that's given. This one may look a little bit more difficult. We have 256. So how can we figure out how we're going to write this? I would start with 2. So you get 128. 2 is prime. And we do it again. We get 2 and 64. 8 and 8. I know that 8 is 2 to the 3rd. 2 to the 3rd. So right now we have, rewriting this 1 over 2 to the 3rd, 2 to the 3rd is 2 to the 6th, 2 to the 7th, 2 to the 8th. Okay, everything else, let's go ahead and take care of the 4 as well, because we're going to get it to be a 2. So it's 2 squared, and it's 3p minus 1. So now on the left side we have 2 to the 6p minus 2, because I had to distribute that 2 in. And then I'm going to rewrite this one as 2 to the -8 power. At this point we have our bases that are the same, and we set the exponents, and we use the inequality as given. So now we would subtract, or we'd add 2 to both sides, and we get p is greater than negative 1. And what we can do is we can plug in a value that's greater than negative 1, so maybe 0, and check this to make sure that it works. I encourage you to check out the additional examples and the additional videos, and also come see me if you cannot do the additional problems on section 9.1.